Assalamu alaikum and hi to Dr. Fauzia and everyone. I'm Fatimah Az-zahra from Group 1 and we would be presenting our mini project titled Thermodynamics in Architecture. So a short brief of it, thermodynamics, it plays a vital role in enhancing energy efficiency, sustainability and comfort in buildings. So we'll explore the advantages and disadvantages of applying these principles in the industry, focusing on their practicality and functionality for developing better architectural products. Before we go further, I'd like to acknowledge my fellow groupmates whose hard work and collaboration have been invaluable. Thank you, and let's get started.
We'll talk about the problem statement of using thermodynamics in architecture. The first one is the integration of thermodynamics into architectural design in order to improve energy efficiency. The second one is we'll look at the potential disadvantages and challenges that it faces when we are employing thermodynamics in architectural industry. And the last one is the application of thermodynamics in architecture design, which contribute to the overall sustainability of the building.
Fatimah Az-zahra here. Now we'll be discussing the objectives of our project. First, we aim to explore the advantages and disadvantages of applying thermodynamic principles in the architectural industry. By understanding both the benefits and the challenges, we can better assess the overall impact on building design and performance. Second, we will analyze the practicality and functionality of these principles in improving building performance. This involves evaluating how thermodynamic concepts can be effectively integrated into architectural designs to enhance energy efficiency and occupant comfort. Finally, we will assess how the fundamental law of thermodynamics, the zeroth, first, second and third, are applied in architectural context. This includes examining their implications for energy conservation, thermal equilibrium, entropy management and insulation effectiveness. Through these objects, we aim to provide a comprehensive understanding of the role of thermodynamics in creating more sustainable and efficient buildings.
Assalamualaikum warahmatullahi wabarakatuh. My name is FATIHAH KHAULAH BINTI ASIDIH and my matrix number is BS221100048. And today I'll be presenting about the hypothesis that we've met through this assignment. And today, as we can see, there are two hypotheses here. The first one is buildings will become more energy efficient and sustainable. So what we mean by this is that the integration of thermodynamics into architectural design can significantly reduce the energy consumption of the buildings. And the second one is about the widespread barriers. So what we mean is that the application of thermodynamics in architecture can bring disadvantages. Disadvantages in what aspects? So in the aspects of cost and complexity.
Now let's go through the advantages and disadvantages of it. For the advantages, it offers improved energy efficiency and reduced operational costs by significantly lowering energy consumption, leading to long-term savings. They enhance indoor environmental quality and occupant comfort by maintaining consistent indoor temperatures, which is crucial for both residential and commercial buildings. Additionally, these systems provide potential for innovative design solutions by leveraging natural energy sources like solar and wind, inspiring aesthetically pleasing and sustainable design. However, these systems comes with initial high costs, including expenses for materials, installation, and integration, which can be a barrier for many projects. They also involve complexity in design and maintenance, requiring ongoing efforts to ensure they function correctly and efficiently. Furthermore, specialized knowledge and training are necessary for architects and builders to design, install, and maintain these systems effectively, adding to the challenges of their implementation. Next, let's delve into how the laws of thermodynamics apply to architectural design. First, the zeroth law of thermodynamics emphasizes the importance of thermal equilibrium, highlighting the need to maintain consistent indoor temperature across different rooms and floors. This is crucial for occupant comfort and energy efficiency. For example, using materials and design techniques that minimize temperature gradients within a building helps achieve this equilibrium. Then, the first law of thermodynamics, it focuses on energy conservation, which is implemented in buildings through insulation to reduce heat loss in winter and heat gain in summer, and energy recovery systems like heat exchangers. The goal is to balance energy input and output in HVAC systems, ensuring efficient energy use. Following this, the second law of thermodynamics addresses entropy in building energy systems, analyzing the efficiency of HVAC systems and the use of renewable energy sources like solar panels and wind turbines. The objective is to maximize energy efficiency and reduce waste energy, ensuring a more sustainable energy flow within the building. Finally, the third law of thermodynamics, though less directly applicable to everyday design, it relates to developing near-perfect insulation materials. These materials aim to minimize heat transfer, enhancing the efficiency of cooling systems and achieving lower temperatures, contributing to overall energy efficiency in buildings.
Findings. There are a total of 4 findings that has been listed. The first one is buildings designed with thermodynamics principle exhibit low energy consumption and higher sustainability metrics. The second one is maintaining thermal equilibrium as per the zeroth law of thermodynamics can significantly enhance occupant comfort and reduce energy waste. The third one is the implementation of passive solar design and effective insulation practice directly aligns with the first law of thermodynamics, reducing the need for artificial heating and cooling. And lastly, the fourth one is successful case studies where tenable thermodynamic principles have been applied effectively, such as passive solar buildings and green roof.
In this part, we will detail more on the implication of thermodynamics in architectural building. One of its implications is economical benefit. We can benefit economically by using the building energy model technology, which can simulate the physics of our building design to assess its potential design, as well as comparing and selecting system and subsystem that are desirable. By having a planned-out design, we could fulfill the energy criteria for our building, and it also could help optimize in the efficient usage of resources throughout the architectural design process. Next, it is also sustainable. This is because it can help mitigate problems such as the urban heat island effect, which is now prevalent in most cities, where urban areas is now experiencing an increase in temperature. One of the effects to mitigate UHI effect would be the usage of modified pavement, which would reflect the sunlight back, though it may experience some temporal albedo degradation over time, as some of the challenges to employing the modified pavement method. Next, it would also affect the occupants' comfort. It could be done so by employing insulation in modern building design, where it could give thermal comfort to the occupant by increasing the thermal resistance of the wall, where it could conserve the energy of the indoor, where it also lead to decreased energy consumption because it does not rely on mechanical heating or cooling. Lastly, it could also pave way to technological advancement. This is because we could improve one of the components in the building design, which is the heating, ventilation, and air conditioning system, HVAC, which could be improved to use a logical control system instead, where it can automatically on or off using real-time data, as opposed to manually turn it off and on. And that is all on the implication of thermodynamics on architectural design.
Now we've arrived to the last part of this presentation, which is the conclusion. So to conclude, integrating thermodynamics into architecture can greatly improve energy efficiency and sustainability. This requires balancing initial costs with long-term benefits. Using thermodynamics principles, architects can design buildings that use less energy for heating and cooling, reducing environmental impact. Future research can make these applications even more effective and affordable, encouraging wider use in the architectural industry.